Okay, we're going to talk about nuclear chemistry. So I'll share my screen. Okay. So we're only going to do a little bit of this chapter, and I'm choosing to do it out of a different text, this free online OpenStax that a lot of you have used, because then I think it flows better if this is what you use for Chem 107. So the reason why we're doing this chapter now is because when something undergoes radioactive decay, which we'll talk about in this section, the kinetics are first order. So it's going to connect us back to our kinetics, our chemical kinetics. So we're only going to do the first three sections: the stability of a nucleus, how you balance the equations, and then what is radioactive decay. The other sections I like to cover in Chem 107. Seems like I haven't had time to in a long time, but if you have time to read section 20.4, it's really, really important to think about nuclear energy and where the energy comes from, but it's not really connected to 108. So this is just showing you some of the uses for radioactive isotopes. So when we talk about stability, we can describe the nuclear structure. We remember it has protons and neutrons, and then the electrons are around the protons and neutrons. And we can calculate the mass defect and the binding energy. So a nucleus is stable because when the neutrons and protons come together, there's a slight mass loss, and that mass equals is related to energy. So Einstein's equation, energy equals mass times speed of light squared. Essentially, that's the energy of that mass defect turning into energy as the nuclei bind. We're going to then explain the trends in the stability of nuclei. So this is just a graph. The straight line would be a nucleus that has an equal number of protons and neutrons. And the blue kind of jagged line that goes through the green is the stable set of isotopes. So those isotopes where the neutron to proton ratio is such that it makes them stable. The green region are isotopes where they're radioactive, so they're not stable. And in those proton to neutron ratios, those nuclei fall apart. This shows you that the most stable nucleus is actually iron 56. So if you have nuclei that are smaller than iron 56, you can fuse those and make bigger nuclei and get energy out. And if you have nuclei that are bigger than iron 56, more protons and neutrons, they can fall apart, undergo fission, and also become more stable. So when we think about how we balance these equations, it's going to be slightly different than how we balance chemical equations. So we have to think about what particles are coming off the nucleus, and then we have to balance the charges. So if an alpha particle comes off of a nucleus, essentially you're losing a helium nucleus. So you're losing 2 protons and 2 neutrons. If a beta particle comes off, you're losing an electron, which has a -1 charge and a mass of 0 relative to a proton or a neutron. Now, we'll think about this more in class, but there aren't electrons in the nucleus. So when an electron is emitted from the nucleus, it's because a neutron falls apart and forms a proton and an electron. So we'll actually balance that equation in class. A positron is an electron. That's another particle that can be emitted from a nucleus. It's an electron with a +1 charge, so it has all the same properties as an electron, but it has the opposite charge. Another thing that can come off is a proton. So a proton can be represented as a P, where you have 1, 1, which means you have 1 proton and 0 neutrons. Or you can also write it or represent it as the hydrogen nucleus, 1, 1. A neutron can come off. So a neutron has 0 charge and 1 mass number. So that makes it a neutron. And then the other thing that can come off and almost always comes off are just high energy photons of light. So gamma radiation is higher than ultraviolet. And we know ultraviolet light can damage our cells and our DNA, give us cancer. So gamma radiation is even higher than that. So radioactive decay, we want to recognize the common modes. We want to identify the particles and the energies. We want to write balanced equations, and then we want to think about the kinetics. So when something undergoes radioactive decay, it would be in that green region, an isotope that's not stable. It doesn't want the number of protons and neutrons it has, and so it's going to fall apart. So in this case, we know that uranium-238 is a common element or isotope within rocks, our Pikes Peak granite, for example. And when it undergoes radioactive decay, it gives off an alpha particle, so it loses 2 protons and 2 neutrons. And so when we look at balancing that, the other particle that will be left behind is thorium-234. So it's going to go down 2 protons from uranium to thorium, and going from a mass number to 238 to 234 means you lost 4 mass particles. So 2 of those were neutrons and 2 of those were protons. This just shows you how we know what kind of particles these are, depending on how they interact with an electric field. So this table or figure is useful, but at the same time, I think in class we'll spend more time actually balancing equations. So this shows you that if your particle coming off is an alpha particle, it's going to take away 4 mass particles and 2 protons. So the mass number is going to go down by 4, and the proton number is going to go down by 2, and that's the new nucleus that will be left behind. With a beta particle, as I said, an electron can come off of a nucleus because a neutron can become a proton. So in that case, the mass number remains the same. Where did my arrow go? There we go. The mass number remains the same. So A is the same, but the proton number goes up by 1 because one of the neutrons became a proton. So just like above, you can balance the charge and the mass. So 4 plus A minus 4 equals A, and 2 plus Z minus 2 equals the same Z. So in this case, A on the left-hand side equals 0 plus A, and Z on the left-hand side equals -1 plus Z plus 1. So in each of these cases, we can't balance the elements like we did with chemical reactions, but we can also always balance the mass number and the atomic number. So I'm not going to continue. I guess I'll do gamma, because with gamma, nothing changes with the nucleus necessarily. Yeah, they shouldn't have changed this nucleus. If it has the same Z, it can't be a different nucleus. So they shouldn't have written it that way. So when gamma radiation is given off, it's just energy given off and not a particle. This is just showing you some pictures of PET scans and how we use radioactive isotopes in the medical field. And this is showing you one of the common isotopes that's a problem in society is radon. So you may have heard of your home can develop a radon problem. So this is a radioactive decay series. Uranium starts at uranium-238, becomes thorium-234, but that's not stable. And it continues to undergo radioactive decay until it reaches lead-206, which is a more stable isotope. In the process, it goes through radon-222, which is an inert gas, and it can filter up into your house. And then if that happens, it continues to undergo radioactive decay, and each of those decay processes, alpha and beta, are very energetic processes, and so they can damage your lung cells, and they're considered, radon is considered the second most important cause of lung cancer, second to cigarettes. This is looking at the idea of half-life. So in our kinetics, we learned that the half-life for a first-order reaction is independent of concentration. So this shows you that the half-life is the same, 5.27 years. So after the first half-life, you'd go from 10 grams to 5 grams. After another 5.27 years, you'd go from 5 grams to 2.5 grams. So radioactive decay is always first order. So we're going to use our LN relationship as a function of time in order to understand how much of any independent or any isotope we'd have present after it starts to decay. And we also know from our first order kinetics that the half-life can be directly connected to the rate constant. It's not dependent on concentration. So the half-life equals 0.693, which is the natural log of 2 divided by K, the rate constant, if you needed the rate constant for the decay. This is an example, and we'll look at some of these in class when we do some problems. Carbon-14 is a radioactive isotope of carbon. It's formed in the atmosphere from nitrogen interacting with radiation from the sun. And so once that carbon-14 is made, and if it's taken up by plants, then it continues to decay. And you can tell the age of something that was once living by figuring out the ratio of carbon-14 to the stable isotope carbon-12. So we'll talk about that in some problems in class. And this just shows you an example of something that's been dated using carbon-14 dating. And that is all we're going to talk about. We'll work more problems in class and actually balance some of these radioactive decay processes and see how they're connected to first order kinetics.